Um, so welcome to the first Hanover series of the season. Of this year, we are kicking off with a very good presenter and speaker, Brent Sohngen. He's from the Ohio State University, and he's the professor of environmental and resource economics in the Department of Agriculture, Environment and Development Economics. He received his doctorate in environmental and resource economics from Yale University in 1996, long time back. Since then, he has been working on land use change, the design of incentive mechanisms for water and carbon trading, carbon sequestration, and evaluation of environmental resources. And if you know anything about forest carbon and then how we report carbon, you would know Brent Sohngen. So he's a well-established name in that area, and he has his own model, global kernel model, to do carbon accounting for the US. And that number is used by EPA to report our GHG emissions. So I will stop here and then let the expert talk instead of me.
Thanks. Okay, thanks, Raju. Thanks. Is that me up there? I don't know. What's up, Frank? All right. Well, thanks for the invitation. I think I'll stand over here. Hopefully that's okay. Yeah, I was trying to think of what the best title would be, so I sort of ended up on this one, and I hope it fits for everything I'll talk about. I will say at the beginning might be a little scattered. I might throw a few extra things in there just because I can at the moment. So, but if anything strikes you as being just wrong today, please feel free to raise your hands and let me know. I've been struck with for a while now this sort of, I don't know, conundrum, if you will, out there that we have in forest carbon. So this is a paper, Gertjan Neighbors and myself and a few others about to come out. And if you look at that, you see this is sort of basically the global forest carbon picture in numbers. It's the land flux. And each of these is a realistic estimate of what that flux might be in the past, might have been in the past, and what it might be right now. And, what strikes me is there's just massive variation, right, in these different estimates. So you've got these bookkeeping models up at the top, the red ones, which are, it's Richard Houghton, others who do these bookkeeping models have sort of made these estimates, and they sort of reckon that forests are a net flux to the atmosphere, mostly due to deforestation, but also due to harvesting. And then sort of these blue lines are these inversion models that use satellites to sort of gauge what the size of the flux might be. And those are all on the opposite side of the scale. So saying that more is coming out of the atmosphere and into forest than the other direction. And then some other numbers in between. So there's a huge amount of uncertainty about this. But it does seem like the central estimate now is tending towards this negative side, meaning that forests are taking carbon on net out of the atmosphere, despite the fact that some big chunk, 6.6 gigatons per year, might be going into the atmosphere from deforestation. So there's a sort of huge sink out there, right? And that's kind of seems to be where the evidence is now, although there still is variation in that. If we look at the US, we seem to have really strong evidence that the US, there is a sink. And, the US seems to punch above its weight. Maybe that's the best way I can think about it, because we have about 8% of the world's forest area, and yet we're about 13% of the net sink globally. Of course, it's trending up, which is getting worse, right? So the sink is declining in scale. But remember, I'm putting most of these numbers into negative terms here because that's the way, we think of it from the atmosphere's perspective, right? If the forest is sucking carbon out of the atmosphere, it's a negative thing from the perspective of the atmosphere, so it's a good thing. So this is a good thing. Of course, as it gets smaller and smaller on the negative side, it becomes less of a good thing. And where does the flux happen when we look just at the US? This is great data from the Forest Service. Grant Domke and others put this together, sort of looking back and trying to sort of allocate flux into, say, three regions: the South, the North, the Pacific region, and the Rockies. And you can see in the South, that's where the biggest sink is in the US, with about 39% of forest, about 64% of the flux. The other two regions, the North and the Pacific, they sequester about the size of their forest area. And of course, the Rocky Mountains, where all the sort of fires occur, and there seems to be more emission out there. So the South is kind of picking up the slack from what seems to be happening in the Rocky Mountain area. So that tells part of the story about what's happening in the US. A different story is some other interesting data that they put together, the Forest Service. And what I did here is break the data into public versus private. And you can see on the public lands, the flux is getting worse, right? That actually, potentially because of the way we're managing public lands versus the way we're managing private lands, which are the green lines, we're getting less carbon sequestration on our public forests and far more sequestration on our private forests, and kind of a concerning picture for the public forest land management in the US. And so this is where the story gets a little bit strange. Apologize to some of you for the next bit of this, just 4 or 5 slides, just kind of a sidetrack from my own perspective, kind of thinking about this public versus private situation. Because the reality is it may never have turned out that way. If you go back a long time ago into the 1860s, this crazy guy, Reverend Frederick Starr, interesting guy, but he's the first one who came up with this idea that there would be a timber famine, that we might actually run out of trees in North America or in the US at some point. He sort of saw this. He was in Missouri, lived in Missouri, he was a preacher out there, and he looked around, he couldn't believe what he saw. What did he see? He saw, settlers coming across the country, cutting down all the trees and turning that land into agricultural land, right? Put it into words. It's a really nice essay. It's about, I don't know, 10, 15 pages long, written in the style that you might expect in the 1860s, so it's kind of hard to read. But this is a great quote, kind of indicative of what he was talking about. Well, destructive man so utterly robs and impoverishes his lands of timber that he destroys the beauty of the landscape. Doesn't, leaves nothing beyond the fence of his woodlot and leaves no shade for man or beast. So it's an interesting sort of idea here that he's looking out and seeing that, wow, we're causing some serious problem here by the way we're treating the landscape. And this is all just private landowners. And of course, we go to sort of Richard Birdsley's estimates, which are kind of phenomenal, right? So he kind of goes back and sort of traces all the cutting of trees in the US. And we know that in the second half of the 19th century, massive increase in cutting of trees, largely to convert land to agriculture, but also just to use it for industrial wood purposes, mostly for energy back then. And we ended up with this massive emission at the beginning of the 1900s. That number, 800 teragrams, is on scale with what happens routinely in Brazil, Indonesia, Democratic Republic of Congo, right? So it was no different here, 120, 130 years ago. Fascinating stuff, right? But what this led to was President Roosevelt looking out in the early 1900s and saying, my goodness, we're heading for a timber famine. It's very likely, given how much we're cutting and how many trees we're cutting, how quickly we're cutting them and converting land to agriculture, that we may end up with no trees left, despite the fact that they're a pretty important industrial product and we might really need them. So he's the first person, publicly at least, to claim that we're headed for this timber famine. We're headed for this sort of time period in which we may not have trees. We may not have enough industrial wood to sort of meet the needs of a growing sort of US economy. Fascinating stuff. So the importance of this, from my perspective, is what this sort of potentially implied for how we should manage our forests. And Roosevelt's sort of initial sort of comments on that had a huge impact early in the last century, in the 20th century. So there were 2 really critical reports that were written. In 1920, the Capper report, and in 1933, the Copeland report. These 2 reports really sort of investigated this question of where are we headed with trees in the US. And what's amazing about it is what comes out of this one in particular, the Copeland report. So the person who was in charge of writing both of those, Earl Clapp, who ultimately became the chief of the Forest Service. He actually was never the full-fledged chief for, I think, 10 or so years. He was the interim chief during the second Roosevelt administration. He really came to the conclusion that, in fact, we had made a mistake. We never should have allowed any of our land to go into the private hands. We should have actually kept it in the public's hands, because the private citizens are just not up to the task of managing forests. What they'll do is just cut them all down and turn them into something else. So he actually advocated to Congress on multiple occasions that private lands be returned to the federal government and managed publicly, and that the public lands continue to be managed publicly. So a pretty strong advocate for that way back at that time. So it's an interesting question to ask is, would we have the same situation today if more of our lands were actually managed publicly versus privately, right? So it's kind of a fascinating situation. I personally argue that private citizens have the right, or have the sort of right set of incentives due to economics to actually encourage them to build a massive carbon stock, right? That the management that we do on those private lands is a big chunk of the reason why we have this massive carbon stock. And I'll try to convince you of that today with some data, hopefully. So just to sort of think back through the 20th century, two things happened that really allowed private landowners to have such a big impact. One is that real corn and soybean prices declined, right? Agriculture became really productive. So that meant that we needed a little less land for agriculture than we otherwise would have needed. And so it released land back into the forestry sector. The other thing that was happening, which was just as important, was this big long-term sort of increase in prices over the 20th century in the forestry sector. So that gave an incentive to people who had forests to manage them a little bit more intensively, right? So they got a benefit out of what was happening in the ag side. That was getting really productive. And they got a benefit out of what was happening on the forestry side, that because we actually were potentially headed for a timber famine, prices were rising and giving people an incentive to more intensively manage their forests. So those two things really had a huge impact. And as the 20th century evolved, of course, we can see in the South, growing stock increased dramatically, huge increases in the amount of forest that we had, not in area, a little bit in area, but not huge increase in area, but mostly just in the size of the stock. And in the Pacific Northwest, where we did decimate old growth forests through the first half of the 20th century, the second half of the 20th century, those stocks stabilized, right? So fairly interesting changes. So how did private landowners do this? So what I want to focus on today is sort of the idea of planting and management, carbon fertilization, and climate change to remain key contributors to this massive increase in growing stock volume in the US. And it's not just in the South. That picture I just showed you had mostly the South, but this is a sort of estimate for the 4 different regions. Pretty much in all 4 of those regions, Northeast, Southeast, Rocky Mountain, Pacific Coast, this is billion cubic meters. I don't know why I didn't put it in the cubic meters per hectare. It's the same, right? You would actually see that the cubic meters per hectare is also increasing in those 4 areas over that same time period. So why is that increasing, right? Why did that increase so dramatically? Because it's a pretty dramatic increase. All right. So now on to the sort of the empirics of the analysis. So one of the reasons might have been the carbon fertilization effect. So Eric Davis and I set out to try to figure out how to sort of identify this carbon fertilization effect in the data. So we decided to try to use FIA data. And Eric had this interesting idea. He said, well, if I think of trees, they're interesting because they live a long time, right? And they're a function of the amount of carbon dioxide they had over that full lifetime that they lived, right? And he thought, well, if I have a tree, I could do this interesting experiment. If I have a 30-year-old tree in 1960, and I cut that tree down, and then replanted a tree in sort of 1990 on the same exact site, and let it grow to 2020. It's the same type of tree, same site, same conditions, right? Shouldn't those 2 trees at 30 years old be exactly the same size, right? Same type of tree. But if they aren't the same size, the question is why are they different? Why is their size actually different? So he sort of thought of this and said, they should be the same size, but maybe the one in 2020 is a little bit bigger. I could use that to sort of figure out something about this carbon fertilization effect, because that's what maybe is different between the two, right? So he decided to try to use the FIA data and to create sort of this experiment that compares the same tree on quote unquote the same site, right? Now we don't always have the same sites to look at, but we can use this concept of matching analysis, which we use frequently in economics, to match sites. To say I can look at a site, say post-2000, with a set of trees on it that are 30 years old, 50 years old, 20 years old, 70 years old, whatever age the trees happen to be. And then I can go into the data and say, look, before 1990, some earlier time period, match the 2 sites. So I'm matching age class, so I get trees of the same age class. I'm matching the same types of trees. So if it's a loblolly forest in post-2000, you're looking at a loblolly forest post-2000 and before 1990, or spruce fir, or white red jack, or whatever type you're looking at, right? So you're trying to match across these two time periods. And you're trying to sort of say, okay, I've got a 30-year-old tree here, a 30-year-old tree there. And then I can test what the effect of the amount of carbon that they actually experienced was. Okay, so he's going to use this matching analysis to do that. Hopefully it works. We'll see. So we tried it out. Basically, he then matched these plots after 2000. So he took all the plots in the FIA database after 2000, matched those to plots before 1990. So we left about a 10-year period out of there, and then estimated this yield function on that data, where the yield function is the log of volume per hectare, a constant, a second term, which is 1 over age, and then we used the log of the cumulative lifetime CO2 concentration that those trees would have gotten. All right. And then a bunch of other things, which are just essentially, site quality indicators. Interestingly, I'll get back to the climate, but actually maybe it's useful to point out what the climate was now. So we matched on climate as well. So for climate, we used seasonal temperature and precipitation. So precipitation and temperature in January through March, April through June, 4 seasons. And then per recommendation by Dave Lewis, who's done a bunch of work with these kind of data, we used both squared terms and cube terms to try to account for the nonlinearity of the weather effects. So we matched on the weather and then included the weather here, or I should say the climate. And we actually use the cumulative historical climate that each of those plants experienced, right? So rather than just using current year climate, since we're calculating a yield function in terms of volume per hectare, which is today's volume, but that's a function of the history and sort of growth that the tree got and the climate it got over its history. So we match not only on this year's climate, but also on the historical climate that that tree got. So theoretically, at least, we've got trees in 2000, post 2000, and they're matched to trees pre-1990 that had the exact same climate. All right, so we've tried to take climate out of the changes that would have occurred between pre-1990 and post-2000. So hopefully that works. The matching actually is pretty good. The paper has the matching statistics in it, and that seemed to work pretty well in terms of the climate. And we think it works in this case because FIA database is so huge. I mean, there's what, 200 some thousand plots, 300 some thousand plots. There's an enormous number of plots. So we're able to find plots that have, 30 years of climate history post 2000 that are similar to climate history pre-1990. Even though climate's changed a lot. So here we're probably comparing, observations from one part of Alabama to another part of Alabama, right? Just because climate has changed a lot over that time period. All right, our interest is in sort of controlling for all this other stuff and measuring this beta 1 parameter. And what we got for the beta 1 parameter is basically 1.1, which tells us that each 1% increase in lifetime carbon dioxide increased the volume by 1.1%. All right, so we're able to detect positively and significantly a carbon fertilization effect, and it's pretty strong, right? That it actually, increased 1.1% for each 1% of carbon. So here we did this for all the different forest types. I don't want to go through each of these. What I'll quickly just go to is we did one regression on all forest groups. So we put all of the FIA types together. This is all sort of 60,000 plots. We have a bunch of 60,000 in the forest groups. Maybe I'll see over here. This keeps coming back at me. My voice is so strong. Okay.
Got disturbed or something.
I disturbed the microphone. Imagine that. Sorry about that. Is that better?
Yeah.
If I dump water on it, it'll quit working.
Yeah, it seemed to me that the microphone actually wasn't working at first, and then it started working, and that's when we had the problem. So I don't know how critical it is.
You mean those people online couldn't hear me? Dang it.
They should be hearing you, otherwise they would have said something.
I can't believe it.
Yeah, well, that's right. They must be great now. Whatever the effect was, it sounds better now. Yeah.
They're all sleeping. Awesome. Okay. So this is the all forest group effect. What we found is that the percentage change, the effect of carbon fertilization between 1960. So what we looked at is between 1970 and 2015 for a 50-year-old stand. So we just used that yield function that we estimated, and then calculated the yield in 1970 for a 50-year-old stand and the yield in 2015, holding everything constant, weather, site conditions, et cetera, the same. And then just looked at what happened with the increase in carbon fertilization or the amount of carbon in the atmosphere. And we found that that carbon fertilization increased yields by 15.4% or 18.4 meters cubed per hectare on average. So that's kind of an average for the whole Eastern US. All of these plots are the Eastern US. There aren't enough Western plots to actually do any calculations for the Western tree species before 1990. So we just don't have enough plot observation data for the Western species, but for the Eastern ones, we have plenty of data. So what you might know if you pay attention to what's happened to carbon over that time period, that there was a huge concentration increase at 23.4%. But for the 50-year-old tree, because of the way we calculate the cumulative amount of carbon that tree experienced, it was only a 13.9% increase in carbon that tree experienced. So remember, the 50-year-old tree was in 1970, started growing in 1920, right? And grew through 1970. And then the comparison tree, which was in 2015, started growing in 1965, right? So the difference between the carbon between 1920, 1970, and 1965 and 2015 is basically 13.9%, which gives you the 15% increase in volume, 18.4 cubic meters per hectare. And if you sort of abstract from this and look at the time period that we look over, that amounts to about 105 million tons of carbon dioxide per year. So it could be that the carbon fertilization effect potentially had or contributed about 25% of the sink over that time period. So significant potential impact just from carbon fertilization, over that sort of 50-year time period. So kind of an interesting result. The second thing we thought about, now, there's one, if you think about this, you might ask, have the ag people sort of done this yet? Have they done the same kind of thing? And if you think about it with agriculture, you can't really do the same thing with agriculture. There's two reasons for that. One is ag's an annual thing, right? So you have an annual crop. It's only experiences this year's carbon dioxide, not 25 or 30 years. So it doesn't have this sort of cumulative effect. And the second thing is that, well, you can't disentangle the sorts of innovations in technology that agriculture made over that 50-year period, right? However, for trees, since we're looking at all naturally regenerated trees, we believe that there wasn't much technology change in the naturally regenerated trees, right? The naturally regenerated ones were simply just trees that survived. So they might have gotten some change due to their ability to adapt themselves, but it wasn't human-caused adaptation, right, over that time period. So we think this works well for sort of natural tree stands and is something we can exploit for forestry that can't be exploited for other kinds of things. But we decided to go ahead and test it for natural and planted trees as well, and just do the same exact experiment with planted trees as we did for natural trees. And the experiment worked out fine. We're able to do the matching. And one of the things we find is that, in fact, actually the proportional effect for natural and planted trees is almost exactly the same, right? So we estimated the same model, but we did the matching on the natural stands versus the planted stands. We did separate matching for each of them. And we find that, the planted stands get about the same proportional effect of carbon fertilization as do the natural stands, which was interesting. Now, when we look at the effect on the volume, this 27% effect, which is the same as a 28% roughly, it's a far bigger volumetric effect, right? So the interesting thing there is that, yeah, carbon fertilization doesn't seem to be having sort of a multiplicative effect with our management. However, from a volumes perspective, because planted trees are sort of improved seed stock, are bigger trees to begin with, right? They're always going to be selected as the biggest trees probably. if you're a person out, I'm guessing if you're a person out there trying to select trees to plant, you're going to select the biggest, best trees. So you're always going to get the biggest ones. So that same proportional effect has a much bigger volumetric effect, right? Relative to the natural stand. The important thing there is that this means that the effect of carbon fertilization on all those plantations out there is far stronger, right? In terms of carbon, because this is, you can translate these cubic meters per hectare into carbon terms. So the point is that it's about the same proportional effect as far as we can tell, but a much bigger volumetric effect. So it could be important from, if you're trying to count the effect of management on the carbon that we've stored in forests, management to the extent that planting is management, could potentially have a really big effect, right? Because of the fact that we've selected these really big trees. Okay, so that just puts it into picture terms. You all get that. Okay, so now the next step of this is to try to disentangle the effect sort of for the whole eastern forest, recognizing that a lot of other things have happened. So carbon fertilization is one thing. So we just tried to separate carbon fertilization out from temperature and precipitation, right? And from management. But management and climate change have both had an effect as well, right? On the carbon in eastern forests. So we want to try to disentangle all sort of four of these things if we can: historical climate, CO2, and management, plus other factors, right? So how have those different factors attributed or contributed to this huge sink we've seen, especially in the eastern US? So we're going to try to do that with data again. And so that's sort of the newer thing here for this presentation. So I guess I say it here. So yeah, this bullet point. So one of the things we did is we did the matching study, and then we did the same exact regression without the matching, and we ended up with the exact same set of parameter values. Not exactly the same, but they're pretty close, the parameters. So it turns out that the matching was important, but really because temperature and precipitation are two other critical things, because they vary across the landscape, and because we can actually control those really well with the historical data we have on temperature and precipitation, because the other site indices are pretty well controlled, we end up with a pretty good prediction of the effect of carbon fertilization, even without all that matching analysis. So the matching analysis was great, but we still seem to get a nice effect, and we're able to identify that CO2 effect just by running the regression without the matching. So the thing is that we just decided to go ahead and use that unmatched regression, right? So we regressed with all the data going back into the 1950s, 40s, et cetera, all the FIA data. We just calculated yield functions, right, for each of the forest types. And these yield functions include the temperature, historical temperature, precipitation, seasonal, and then those cube terms, squared terms, et cetera, on all that. Have all the site-specific indicators, elevation, soil types, aspect, et cetera, et cetera. We included the log cumulative CO2 that each tree experienced, given the age it was at the time period it was observed. So we just estimated this thing, and then we calculated for we did it separately for the naturally regenerated stands and the planted stands. And then we were able to look at, between 1960, for example, here in 2017, the change in climate and the change in carbon dioxide, and just sort of assess whether it had different effects, right? What the different effects of them were. So here for an oak hickory stand, for example, we have a yield function with all those parameters in it. And for the climate effect, what we did was hold carbon dioxide at 1960 levels and hold everything else at 1960 levels. And then for each observation where there's an oak hickory stand, we just compared the climate in 1960 to the climate in 2017, right? And gave, calculated two different yields for that same site, right? One in 1960 and one in 2017, and then calculated the average difference across all 100,000 observations of oak hickory. And we found that climate, the observed climate changes that happened between 60 and 2017 for 50-year-old stands led to a 42% increase in the volume, or 32 cubic meters per hectare. CO2 effects were 19%, 18%, and 18% for the loblolly, right? So we did the same thing for oak hickory, maple beech birch, loblolly, for all the different types, right? So this is just an example of them, and showing that for these three species at least, the climate effect over that period was largely positive. And well, it was entirely positive on average for these sites. And the CO2 effect was positive, and the combination of the two was positive as well. We then can map that out so we can see that it wasn't positive everywhere. And the interesting thing is we could also test the precipitation changes separately from the temperature changes, and then add in the CO2 fertilization effect. So for example, with oak hickory, you can see with the precipitation effect. So here what we did for that particular example is we only changed precipitation between 1960 and 2017. Everything else is at its 1960 level, all right? So the effect here suggests that somehow there was probably less precipitation in these areas where it's yellow, more precipitation in the areas where it's blue. We did the same thing for temperature. So you can see temperature changes are probably higher in those other areas, less high in the blue areas. But then when we add the carbon fertilization effect, that sort of washed out any of the negative effects of the climate changes, of the temperature and precipitation effects. Loblolly, similarly, you can see precipitation probably was not enough up here. Of course, this is fairly far out of the zone for loblolly in terms of historical temperature. So maybe that also might explain to some extent why precipitation changes had such a negative effect there. See temperature changes a little higher in the south and had a negative effect there. Okay, so you can actually show sort of geographically where these changes happen across the time period from 1960 to 2017. That's kind of fun. This again, the same graphs, just added in oak pine, but the averages here suggest that climate did increase wood volume 17 to 42%, although some types of spruce fir had an actual reduction, and carbon fertilization increased wood volume by 17 to 20% over that time period. So climate change over this period was largely positive for forests, and when combined with carbon fertilization was always also positive. So these two things seem to have a positive effect and would have contributed, both of them positively, to the observed sink that we had, right? So the last thing we had to do was sort of try to figure out whether there was an effect of management and add that in. And so for this, we only looked at 3 species. There's only 3 species out there in the eastern US that have a significant amount of management in them, and that's, you know, loblolly, shortleaf, longleaf pine, and then white red jack pine. They're the only places where we have observed a large enough set of planted stands. Okay, and so what we do for this is we actually just put in a dummy variable for whether the stand was planted or not. And the dummy variable with that large sort of regression, large set of data tells us sort of the proportional effect of planting versus the other things, climate, CO2, et cetera. And we found that planting was largely positive as well, and up to a 35 to 40% increase in volume. Okay, so kind of have these yield functions. Now we're thinking, okay, how do we actually use this to figure out and really say, you know, because what we wanted to do was say how much of this 700 million tons per year is due to these different things. And we haven't quite got there yet. So we're trying to figure that out. So the next thing we did was say, well, you know, we can only do this maybe for a certain place like the South. So we went into the South and said, well, the nice thing about the South is that they had inventories that were taken in the 70s. So every one of those states went out and collected, you know, plot level inventories in the 70s. So we have a relatively good estimate of what the age class distribution, the area of each of those forest types was in the southern US. So we took those southern states, and there's 12 of them, and we started with their inventories in the 1970s. And we used our estimated yield function to then predict their volumes for the inventories in the 1970s, right? So for each of these states, we had their 1970s sort of inventory. And then to try to disentangle the effects, we said, well, let's hold each one of the other things constant and just change one thing at a time and see how much extra volume we get or how much less volume we get, depending on the size of the effect. So for example, for the age example, right? We basically took each one of those forest types. You could think of oak hickory. We took the age class distribution in the 1970s. We took the climate in the 1970s, the carbon dioxide level in the 70s, et cetera. We calculated the yield function. And then we imposed on that, those same set of yield functions, we imposed a new age class distribution that we observed in 2017, because we have the 2017 FIA data as well, right? So that will allow us to see what the effect of a change in the age class distribution is on the volume, right, of trees. Same thing for area, same thing for climate. So when we look at climate, we're going to hold age, area, CO2, and management constant. So does that make sense? So we're just trying to sort of figure out and test or assess what each one of these individual changes would have done to the volume of trees over that, 40 to 50 year period. Okay, so this is what it did. We can look at each of them separately for each sort of type. I'm not going to go into all the specific numbers here. We'll look at the bottom numbers here in a second. But just to notice that, for some species in the South, like elm ash, cottonwood, they went from an older age class distribution way back then to a younger distribution today. Same thing with oak gum. The rest of them sort of all went to sort of older age class distributions, and that contributed to the increase in volume that we have today. Same thing with area. We see some types had reductions in area. Some types had increases in area. You have to be really careful here. One thing we know happened in the South was a removal of slash and longleaf and oak pine and conversion to loblolly. So that's why you had negative for oak pine and slash longleaf and pretty big increase in area for loblolly, climate, et cetera. So let's look at the aggregate numbers here. So in total, age class, increases in age classes in the South contributed 465 million cubic meters of volume in the South, right? So the volume just increased that much as a result of just an increase in age classes, all right? A loss of area, when we net out all of the different types, there was a slight decrease in forest area in the South over that 74 to 2017 period, and that led to a reduction in the total volume of trees in the South. Climate led to an increase, 897 million cubic meters. CO2, increase in CO2 led to 960. Planting, 455, for the total change of about an increase of 2.7 billion cubic meters of volume, right? So you can sort of then disentangle and see that age class, an increase in age class was important, but climate, CO2, and planting played as big or bigger of a role in the observed sink that we had over that sort of 30 to 40 year period. Breaking it into proportions in total, 17% age, 34% climate, 36% CO2, 17% planted. If we just look at softwoods, then it elevates the effect of planting. So it turns out that management is a pretty important effect. Potentially 17% of our total sink in the US, in the South at least, is resulting from just our management of those forests, right? With climate and CO2 playing an important role as well. Okay, so that's the South. This is to compare, actually just quickly on this one, this is the actual change that FIA estimates, and this is our predicted changes that we just showed you. So we're relatively close. We're not exact. I don't think we could ever be exact with that. And there would probably be some interaction effects between climate, CO2 management that we're not accounting for yet, that could be in that difference. But that's just pointing out that they're pretty close, and at least we're in the right direction on each of them. Did some valuation of that. See, and our estimates suggest that management added something like 29 billion in net value to land value, and carbon fertilization an additional 28 billion. So pretty significant effect of both of those two on land value in the South. And then we looked at the north. The north is different for a lot of reasons, right? But we don't have as many older inventories in the north, so we can't go back as far. So we decided to just use the period over which we've had the repeated observations. So FIA changed in early 2000, right? When they went to the 5 or 6 year cycle in all the states, where they remeasure the plots every 5 or 6 years. So we're just using that data because we have the most data. And this actually turns out to be really interesting, actually. So what we found, so we did the exact same test, right? We have the same yield functions. We're only sort of doing it between 2001 and 2017. Same analysis, just a different set of states. And here, you know, what you can see, again, going across, and this is age, area, climate, CO2, and then a little bit of management. The north stands aren't managed nearly as much, so management's a much smaller effect, but still a positive effect in the north. But what I found super interesting in these results is that, you know, largely the climate effect between 2001 and 2017 was mostly negative, right? So if you remember back way earlier estimates, go back those earlier estimates, the effect of climate from 1960 to 2017 was mostly positive and pretty strongly positive. So it does look like, based on these results and based on our estimates, our yield functions, and the observed climate changes, that we potentially have shifted in the Northeast to where in the last 20 years, climate's having a negative effect, right? So any positive effects we got for the first, you know, for 50 years, 40 years or so between 60 and 2000 have been dissipated to some extent by more negative effects more recently. So that was actually kind of surprising to me, interesting. I don't know if surprising, but it was just interesting. I guess I hadn't expected to see that because we've been playing around with this 1960 to 2017 data for a long time. And all of a sudden the 2001 to 2017 was saying kind of something different. So that's interesting. We'll probably try to tease that out a little bit more. You can see sort of in the north, the effects, you know, area and climate. And of course, in the Northeast, we have another factor, which is that we're actually losing forest in the Northeast a lot more rapidly than in other places, mostly to suburbanization, but it's definitely happening and having a noticeable impact. And so far, though, elevated CO2 and planting are kind of have outweighed these things over that time period, but who knows how long that'll continue to last, right? So the final thing we did here is sort of look into the future and say, can we take these estimates, these both climate change impacts and CO2 effects, and project them forward and ask the question, what might happen in the future? So we did that with this sort of global timber model. We project just with prices, some modest price appreciation, nowhere near like what we saw in the last century. The US South does continue to plant trees, but because prices aren't increasing as much, we see a lot less planting. So there's a lot less conversion of natural stands to planted stands in the South. So potentially slowing down the sink there. Same thing happens in the rest of the world. And we see that the sink in the South starts to dissipate in the next 30 to 40 years, although it increases by mid-century. Although for the US as a whole, we project that the sink continues on and becomes a little bit stronger mid-century. Our projections go out further and it gets a little bit weaker later in the century, but does continue to sort of strengthen. So we sort of see that if we take these projections and continue them out, that the US sink remains relatively strong in the near future, but and that does include the effects, the negative effects of climate change in the Northeast as well. So those are important, but they don't have sort of get offset a bit by what happens in the South. Okay, so in conclusions, private land is where most of the action is in forest, and it has led the way in providing timber products, forest stocks, and carbon. So these results seem to suggest that management's been really important. And what we haven't been able to do is to show that there's a real, that people, well, what I suspect is also happening is that, you know, we're probably over-attributing, well, I don't know if we're over-attributing, but I feel like there's a lot of effort out there to say that management has increased stocks of forest dramatically, but I think we're actually, people who manage forest maybe are seeing carbon fertilization effects because the carbon fertilization effect has been so strong. and it's certainly helped management be pretty successful, I think. So far, we think they're about equal shares of the volume in the South, and are both important for the size of the sink. Management can be credited with about 17% of it, or if you look just at softwoods, about 30% of the total carbon flux. And I guess a growing concern that climate change is now having a negative effect in the North, at least on our carbon sink, right? Lots of other potential negative effects, but for sure on the carbon sink. So with that, I'll stop, I guess, and open it up to questions, comments. Whatever.
Question, comment? You know, the first thing I think of when I'm sort of trying to wrap my head around your incredibly interesting sort of big picture takeaway, I'm still trying to square it with the sort of conventional wisdom about forest regrowth across the eastern forest, right? And so I realize your analysis wasn't able to look in the Northeast at that part before 2000, right? So, I mean, is there any, do you have any sort of comment or idea about like what the ballpark is when you look at the carbon sink going back to 1960 or whatever? I have to imagine that, you know, growing forests in the Northeast are having a big contribution to the overall carbon sink.
I think for sure yeah. Well, I think for sure that they were. I think actually what's happened is that between say the 1950s and 1990s, the Northeast was the biggest chunk of the U.S. carbon sink, and I think that switched in the last 30 to 40 years, where the South has become the bigger chunk of it. I think a lot of it has to do with management because of replanting, and less management in the Northeast as well. But also, I don't think we can dismiss the potential effects of climate change also diminishing that it's actually, you know, maybe unnoticed, maybe it is noticed, I don't know, but it's just less discussed. That, I mean, if I look at reports by the Forest Service and others as to why the sink is diminishing in the Northeast, usually I hear the age class changes or what's causing it. I don't see any evidence of that. Actually, age classes aren't that much different as far as I can tell from some of the FIA data. But what does look to be different is potentially climate. So I don't know, that's kind of consistent with your thought, I think, that it was a big sink, but it's now sort of diminished.
If you don't mind me adding a follow-up, you know, I'm of course thinking also that the Western forest wasn't the focus of your analysis. Right? I would imagine, of course, very different results there where you see strong negative climate effects in the W. Yeah, I mean, what do you think about that? Or have you, is that something you?
Yeah, yes and no. I mean, so one of the things we've got data from Alberta, and we're working with that right now. So it's not the Western U.S., but similar slow growing forests, actually slower growing forests, right? So boreal forests in Alberta. But, you know, they have these fantastic, you know, industry was actually collecting samples and plot level data back in the 60s and 50s and 40s. So we have really actually old, you know, several thousand plots that are repeated over time. And it is more difficult to disentangle the carbon fertilization effect there, in part because of, we think, the signature of fires. So Canada also has fire perimeters going back a long way, so we're able to actually match those fire perimeters, and we can detect some of the effects of those fires. So it is plausible that these other sort of disturbance effects that you need to control for them carefully. So that's actually one of the things we controlled for in the matching analysis. So we think we've got that handled in the East, but it is more complicated in the West. So there's probably even longer term things that would make it more difficult to sort of detect. Yeah. So maybe it's fortunate that we don't have enough old plots in the West, so we can't act like we know something we don't. Well,
thank you.
Yeah, thanks.
Thank you for a great presentation. So my question is that so you took a look at the difference between the managed planted versus natural regeneration. Are they like a confounding effect with private and public, like most private lands are for with planting compared to the natural?
Yeah, we do control for that. So in the first analysis, we actually dropped all of the public land observations. So we didn't include any of those because we were afraid of that there might have been some inherent bias in that because of the types of lands that the public has versus the private lands. In the second analysis, we didn't drop those. So there may be some confounding effects there, but we do control for that. We do control for ownership, right? So it's a control. But there may be something in there that's because, yeah, I mean, it's in the West, it's the lands nobody wanted, right? They're the least productive stuff. And in the East, I'm presuming that the lands that would back into the federal coffers probably was the least productive forest land. So there could be some effects there that in the sort of the second analysis that, well, the first one, we dropped all those public lands to specifically to keep that out. Yeah.
Did you have like economic perspective that's planting trees pays off compared to the volume that's increase over the time compared to the how much it's cost to plant trees and at the end in 50 years it's the pays off.
So yeah, in the sort of dollar numbers I showed, we did account for the cost in that of planting, but that's we don't have plot by plot planting costs, right? So those are just basically based on this planting costs were assumed to be the same for every plot, although they did change over time based on surveys. Plenty of people have done surveys of planting costs at different time periods, so they've gone and surveyed ownerships of people who plant trees. So, we know like in the 1980s, what planting costs versus the 90s versus the 2000s. So that was included in that economic, sort of quick economic analysis, but it's not plot by plot because we don't know individual ownerships or individual plots planting costs. It'd be awesome if we had a database of that, but we don't. Yeah.
Okay. I think let's go to the June. So we have a question from the who's asking. What climate variables were being considered and where these just averages or also variability?
Yeah. So so for the climate variables, they are averages by season. So it's the average over the lifetime of the tree. So if the tree in 1960, for example, was a 30-year-old tree, it was the average temperature that tree experienced in springtime, wintertime, summertime, or fall. And then to try to account for the variability component, we use these squared and cubic terms. I don't think that's a perfect measurement. Actually, then, in addition, for the first analysis, the matching analysis, we did include vapor pressures and a few other variables in there that were that the PRISM data has to try to account for some of the other things besides just temperature and precipitation. And a reviewer was really insistent on that, which was great. I mean, it helped out. So, but I don't think we probably could do more on it's interesting. I guess, well, the ag literature is pretty specific about that. That crops are particularly harmed by really hot weather, right? By a number of growing degree days above like 90 degrees or something like that. That can really dramatically reduce yields of corn and soybeans. We didn't test that with trees. That would be something to test.
Yeah, no, thanks for your answer. I was just sort of wondering because I was thinking that things like some of the more recent heat waves and periods of corresponding water deficit in the soil, might be important to some of these dynamics, but thanks for talking more about that.
Yeah, that should definitely be on the list to test out. I don't think it affects the carbon dioxide analysis because we're really just trying to match that. But the second analysis where we're trying to use it to predict changes, yeah, we should probably be a little more careful on that.
Thank you.
Thank you. So let's go to Larry and then Scott and Mike. Larry, please give it a.
Hello?
Yeah, we can hear you, Larry.
Yep, Larry, we can hear you.
Oh, okay. I'm sorry. I wasn't sure if someone was moderating.
No, Raju was
the-
talking, but he didn't have a microphone. Sorry about that.
Okay. Okay. Very good. Yeah, first of all, thank you for the presentation. It's very interesting and a topic of great interest to the audience here, certainly, and many others. One thing that is a comment, is that in agriculture, I think that when you plant an acre of corn, that's until you harvest it, that's about it for management. But in forestry, there are a lot of other potential activities that may take place. So I think words have meaning. And so I think you have to be careful of equating planting with management. That's just a general comment, and you can give some thought to that later. The question I have is that another aspect, I think, I'm not a Southern forester, but I think that genetics has played a role in selection of stock for loblolly and so on over the years. And so the tree planted in 1960 is not the tree planted in 1990, other than by name. And so have you given that any thought and how that might affect these sorts of results? And so I'll look forward to your response.
Yeah, and thanks for that comment. And yeah, guilty is charged on the management versus planting. That's a consistent problem I've had here. So in the writing, it's entirely refer entirely to planting. And that's probably how we should refer to it, because that's really what we're looking at, is the effect of planting and relative to naturally regenerated stands. And then to your point on the changes in sort of in how people have selected trees for, you know, future generations of trees. Yeah, for sure that was a driving motivation in the first study we looked at, and for breaking these into naturally regenerated versus planted stands, because we believe the naturally regenerated stands don't have that quote unquote problem that people are selecting more quickly than nature would, you know, the stock that they're regenerating. So we're trying to wash that effect out. And so we think that by just looking at naturally regenerated stands over the sort of 50-year time period we're looking at, that probably it's unaffected by any technological changes that humans would cause. So there's a little speculation there because we don't know, right? Of course, people have gone out and done things in hardwoods and other kinds of things, but we think it's pretty modest compared to, say, with loblolly. And so therefore with loblolly, we did try to focus just on the natural stands versus the planted stands separately. And we're surprised to see that the effect of carbon fertilization was proportionally exactly the same for the natural stands and the planted stands. That was kind of surprising, I thought. I mean, it was reassuring maybe to see that, to suggest that despite the fact that, you know, people have gone out and have selected different types of trees over time, and that you're right, what we're planting in 2000 are different from what we planted in the 1960s, but that the CO2 effects seem to be the same size proportionally for those. Different effect in terms of volume, but proportionally the same. So that's all I'll just say. I totally agree with everything you said. We tried to control for that, hopefully successfully, but you know.
Thank you. Thank you.
Yeah, thanks.
Anybody else? Oh yeah, I just had a short point, I guess following up on Bailey's comment. It's interesting for me to think about this in context of the debate I follow a lot, which is the carbon sink debate in the Amazon forest. So I wonder if what's going on in the Northeast might have some parallels there. One thing that shows up as a driver of changes in the decreasing carbon sink in Amazon, the impacts of droughts, and also just generally cumulative water deficits. So that's a nice variable impact that shows up as being really volatile there. So I was looking at your temperature effects in the Northeast and wondering if it's like these forests are starting to see water deficit that they have, or this is the effect of the increase in energy.
Yeah. Yeah, just one thought on that is that one of the things that we've really searched for and tested is whether there's an attenuation effect with carbon fertilization. So, because many people have suggested there's like a saturation effect with carbon fertilization, and we haven't found that in anything. We found that older trees proportionally are getting the same effect of carbon fertilization as younger trees. So we found no attenuation. So, but I think, that nonetheless, in the Northeast, we see a reduction in the carbon sink as a result of climate change. So, that's not, carbon fertilization effect was still positive. So older trees were still gaining from carbon fertilization. It's just that the climate effects were worse.
Yeah.
And we're detracting. I think it's the same thing in the Amazon.
Yeah.
And I think that's what the modeling studies have shown is that, even those quote unquote old growth forests in the Amazon, right, even though they're not really necessarily old growth, they're susceptible to disturbance and everything like that, that their carbon fertilization is still positive and strong, but other factors are detracting from that, and potentially the net effect could be negative in some places.
Yeah, I mean, big droughts.
Like El Nino driven droughts, et cetera. Yeah. Yeah. Interesting. Yeah.
Yeah, maybe, let's skip this. You want to comment on Mike's comment? No, yeah, before we go.
I'm just reading it. Sorry. Yeah. So Mike, I looking at your comment, I guess it's an interesting thing. I think one of the, I think one potential takeaway from the example of the Southern US is that, that it's not, actually producing wood products and producing carbon are not incompatible. The strongest sink in the South is actually those planted pines. And it's because they're planted and because they're such big trees and they get the same carbon fertilization effect. And they're also, planting them in places that are a little more adapted to climate change. You can actually trace and see that they're starting to plant things further north. Actually, you can see this happening in the South. They're changing where they're planting loblolly in the last 50 years. And it's to adapt, I think, to climate change. So I think the reality is that we can have both of them. It doesn't mean we're gonna have all the other ecological services, right? We heaven knows we wouldn't want the entire country to be planted in southern pines, right? That would be awful for all of us, I think. However, it does mean that if we have 30 million acres of it, we're gonna have a significant product pool as well as a significant carbon sink, right? So these are not incompatible.
Thank you.
Okay, so thanks, Brent. That's fascinating presentation, and I particularly like your research design, bottom up, plant level, based matching approach. I think this is understanding, and also the results are so interesting. A couple of minor comments, perhaps a small question as well. First, I wonder what you didn't consider to, at least at the regional level, have some average annual climate change effect, estimated, so that we can have a different way of understanding the longer term effect. And plus, because the data coverage has different shifting data periods, if you can have a consistent, clear bottom line, the annual gain would be so much, 1 point or 0.5%. In terms of volume, that would be, I guess, more insightful. Plus, I compare this work with the earlier paper, which is based on a top-down approach, uses the global vegetative color model, which gives you an annual rate of 0.04%. So that's what I suggest to your comment. The other one is you mentioned the earlier abandonment of Adelaide. Wouldn't you think is the residual fertility of those abandoned Adelaide would go up for the growth a little bit? Or, I wonder if you have factored that into your assessment.
Yeah. So on the first point, that's a really good one. So one of the things like we've got to do with that is that you showed those pictures of just the temperature and the precipitation effects, but actually we should probably not show those in terms of the actual temperature and precipitation effects, because that does confuse things, right? That there's the how do trees respond to a temperature or precipitation of change on average? And then there's the question of how did temperature and precipitation change across the landscape, right? And there's kind of two different questions, right? And that was kind of mixing the two up. So it is confusing to look at that. I agree with. Then the second thing is the residual. Yeah, that's an interesting question. I don't. So I guess the point is there residual? So when you move from ag land to forest land, if you replant trees, southern pine trees on old ag land, then maybe there's some residual nitrogen and phosphorus in the soils, right? That's there that helps the trees grow a little bit more quickly. We didn't control for that. We should actually probably test that out with by trying to test for the recency, if we can, of that plot having converted to trees. We think most of these plots are, well, we know most of them aren't recent converters, right? Most of them were converted in the way past. But we think that's not evidence. So that's a good point. We do need to test that. I've been asked that a couple of times. We need to go back and test on that. I'm trying to think of a way to do that with the data that we have, which is FIA data, which doesn't have that sort of, when did this get converted to trees, right? So that it's complicated to think about how to do that, but that is an interesting question, right? I doubt it's as important for nitrogen as it would be for phosphorus. For nitrogen, it's more of a flow thing that doesn't stick around as long in the soils, I don't think, as far as I know from agriculture, because they have to put it on every year, but phosphorus does. So.
Okay, I think, Brent, we are out of time.